ZeroReducers. We have seen combiners, counters, and compression. Other tools. If there are slow tasks, then we can run several copies of the same task together. So if we want to do that, we can specify this in the configuration, and we can say speculative execution. If we say speculative execution, then if a task starts running very slow, we will have multiple copies of the task running. Sometimes we only need to run a filter on the input data. If that's the case, we don't require shuffling or sorting on the results, and we just want to run a filter on the input. If that's the case, we can say reduce. We don't want reducers. We're only going to have mappers. If we don't want the reducers, we're just going to say set the number of reducers to 0. And if that's the case, the output from the mappers will go directly into the output format and to the disk. The cache. So I mentioned that to speed up processing, we can cache some of the data. So if we're not going to be writing anything, if it's just a read-only copy, we can download it into the local machine, and we will have a copy of it instead of having to go and get multiple pieces from the network that are located in several different places. We can download it up to 1 gigabyte and store it on the local machine that the mapper is running on, and that's called DistributedFileCache. So then we can define the list of files we want to download in this job configuration, and they are downloaded once per that computer. So distributed cache, add cached file, and then we say the path to where this file is located, and add it to the particular task. About the standard command line options. So we have a tool to handle the standard command line options. That will be extend the configurations and implement tool. And in that case, this is, let's say, we want to give, during the processing, we want some input from user. It will allow us to give command line commands through the command line for that program when it's running. So we have seen word count example for MapReduce. But we said that Google was using a MapReduce. What do they use it for? So we said computing PageRank. Can we use MapReduce to find the shortest path in a graph? Let's imagine that this is a graph of web pages, and these lines are showing which page has a link to which other page. And so if we want to compute, let's say, how many links each page has and what other pages is it pointing to, then we can do this graph processing, and it can be done with MapReduce. Another application is to find the shortest path from one node in the graph to another node. This could be used for routing, for example. Let's say this machine wants to send a file to this machine. Is it going to go this way, or that way, or that way? what is the best path? So if we want to compute the shortest path, or optimal path, or the fastest path, or the best path, then we could use this famous Dijkstra's algorithm and see if we can implement it in MapReduce. How are we going to do this? Let's say we want to compute the shortest path in terms of distance, physical distance, and so then we will use the distance to the start node equal to 0. All the nodes that are directly connected to it, we will set distance to 1, and the nodes that are reachable, we will set their distance to some number s. And then we have a formula. We want to take the minimum distance to get there. So every node will have some information about its neighbors that are directly connected to it, and what is the distance to those neighbors. So the map task will receive the node as a key, and then what other nodes does it point to will be the value. Or what other nodes is it connected to? D is the distance to the node we are trying to reach from the starting node. And point 2 is a list of nodes that can be reached from our current node. So this is what the mapper will do. It will take the list of nodes that are reachable, and it will take the distance, and the reducer task will gather possible distances to a given node and select the minimum one. So what would this produce? The MapReduce task will advance to the node it will advance by one hop at a time. One hop means go to the next node. A non-MapReduce component will feed the output of this step back to the MapReduce task for another iteration. Now, unfortunately, we have an iteration. This algorithm is iterative, the Dijkstra algorithm. And like I mentioned, the MapReduce, when we have many iterations, it doesn't perform all that well because it has to keep scanning the data every time for every new iteration. But we do have iteration here. So the output of this step back to the MapReduce task for another iteration until we reach the destination. So what happens is we have the first node, and it only has information about its neighbors. So it's going to choose one, the closest one, and that's the next node that it goes to. That node has also information about its neighbors. It's going to choose one, the closest one, and then we go to that node until we reach the destination. Every time we get to choose another one, we have an iteration for the MapReduce task until we reach the destination. So the mapper will emit a list of points and the nodes that we are trying to reach. When are we going to finish? Eventually, the routes between the nodes will stop being discovered, and there will be no better distances found. When the distances no longer change, we will stop. So each node might get updated distances in case something happens. Let's say one of them is no longer there, or the distance changed because one is no longer there. And if that's the case, then the distances will no longer be updated. So we will choose one distance, the shortest distance, until we reach the destination. When we reach destination, we will stop. So we have the node we're trying to reach and the current distance. That is what is carried on to the users. There are some sub-projects of Hadoop. MapReduce is one of the most common ones that is being used, that runs on the Hadoop over Hadoop system. So Hadoop is just the cluster configuration program that manages the cluster of computers, the data that is being stored on them, manages the distributed file system, and we can have programs that run on top of it. One of them is the MapReduce. Another ones are all of these. Here is again created by with some high-level language for data analysis. HBase is a system for storing data similar to a relational database management system, but it's on the cluster, and it can store data that's not necessarily in a raw column format as a table. That's called same structure. Let's say there is XML file. So the XML file has tags similar to the HTML file. And the tag says customer, name, salary, something like that. Well, we don't have a table that says here's your customer on the row and here's the salary in the column. But we do have a text file, but still there is some information about that this is a customer, this is their salary. So that's called same structure. Zookeeper is another platform that runs on the top of the Hadoop that coordinates distributed applications. So it does it's another platform that speeds up processing and reliability. So it takes care of failed nodes in its own way. Hive is a system where we can load data into tables and run queries on them. So it will accept queries in similar to SQL queries. And this is a tool that can run on top of the Hadoop platform that allows us to do machine learning. Let's say we want to do clustering or decision trees and things like this on top of